right, so in addition to specific heat, we've also got heat capacity. So specific heat tells you how much heat I have to add to something in order to raise the temperature by some amount. Heat capacity tells you more or less how much heat I can store in some material. And so for different types of gases, I have different heat capacities. So this is for a 3 halves R is for a monatomic gas, and CV is equal to 5 halves R for diatomic gas. And then CV is equal to 3R for a solid. And so the difference between these two has to do with the number of degrees of freedom. These aren't degrees of freedom like those granted in the Bill of Rights. These are degrees of freedom in terms of movement, right? So for a monatomic gas, right, you've just got one little particle, and it can go up and down, left and right, forward and back, right? But for a diatomic gas, where I have 2 particles connected together like that, a molecule, then I've got an additional rotational degree of freedom like this, as well as a rotational degree of freedom like this. So I've got these 2 additional rotational degrees of freedom. And so I add those 2 additional rotational degrees of freedom to my 3 translational degrees of freedom, which I also still have for the diatomic gas particle. And so that's how I end up with this 5 over 2 instead of 3 over 2. Each one contributes 1/2 R. Right? So with 5 degrees of freedom, I get another 2 halves R to add to my C. Okay. Well, thank you, buddy. Appreciate it. All right. So that brings us to heat and work. And thermodynamic processes. And so with that, I'm going to draw a PV diagram, which you should be familiar with at this point, right? Where we have pressure along the vertical axis and we have volume along the horizontal axis, right? And down at the origin, we would have 0 volume and 0 pressure. And what I'm going to do is I'm going to draw a thermodynamic process. So let's say I start at this particular state. So each point on this graph represents some particular state of the system. Right? So I have a combination of pressure and volume. If I relate that back to my ideal gas equation, I have some combination of pressure and volume gives me some unique temperature. As long as I don't change the amount of gas, N, right? N is representing how much gas I have. As long as I don't change that, and I move somewhere on this PV diagram, all I'm doing is, well, not necessarily all I'm doing, but I'm changing the temperature, right? The temperature is changing if I change the pressure or the volume, possibly, depending on what kind of process I have. Okay, so let's say I have some imaginary process where I go from this pressure, I'm going to call this one P1, to some other pressure, P2. And I go from this first volume, which I'll call V1, to some other volume, V2. So maybe I follow a path in this thermodynamic process, something like this. And so I go from state 1 to state 2, right? And I follow this direction. Then, if I want to figure out how much work is done in this process, then essentially what I want to do is integrate underneath this curve and get this area. And that's going to tell me how much work is done. What do I mean by how much work is done? Well, work is equal to integral from V1 to V2 of P dV. So some varying pressure that I integrate with over the volume, right? So that's really just what I'm representing graphically here. That's just the mathematical version, right? So the work done is the area underneath that curve. If I'm going from some smaller volume to some larger volume, and I have area underneath my curve, then the work done is work done by the system, work done by the system, and it is positive. If, however, I went in the opposite direction for this process and I went from some larger volume to a smaller volume, then I would have a negative work, right? As long as I have a positive pressure, I can't have a negative pressure, right? We don't deal in negative pressure because again, it's absolute pressure because absolute pressure starts at 0 and goes up. There's no such thing as negative pressure in a absolute pressure system. Now, if the pressure is constant though, right, so this is a varying pressure, but if I have a constant pressure, then this integral simplifies to pressure times V2 minus V1. So that's for constant pressure only, not for all situations. And so the way that we define the sign again is that W is positive for increasing V, and W is negative for decreasing V. So that's what I was saying before about the direction of my thermodynamic process. Okay, so that's the work. We'll get back to the heat in just a little bit. So let's do the first law of thermodynamics. All right, so the first law of thermodynamics says that delta U is equal to Q minus W. Delta U is change in the internal that's the change in the internal energy of the system. Q is still the heat and W is the work. All right, so another sign convention here is that Q is plus for heat added to the system, and W is positive for work done by the system. So you have to be very careful in these problems when we're talking about work done on a system or work done by a system and heat added to a system or heat removed from a system about the actual prepositions that we're using in those questions, right? Because they matter in terms of what signs you use for Q and W. So changing internal energy, right? If I add heat to the system, that's got to increase internal energy, right? If I dump some heat into the system, that's got to increase internal energy. So it makes sense that it's positive because a positive Q should lead to an increase in delta U, right? If I don't do any work, if work is 0, I just add Q, that should increase U, right? If there's no heat added or removed from the system, so Q is 0, but the system does some work, right? It does some work, it changes volume, does some work, but there's no heat added or removed from the system, right? What kind of process would that be, first of all? What's that? Adiabatic, right? If there's no heat removed or added to the system, and it does some work, that's an adiabatic process, right? And so then I would just have work done by the system. So if the system does some work, it must lose energy, right? So there must be a decrease in delta U, so it makes sense that for work done by the system, minus W, minus a positive, must lead to a decrease in internal energy. So you can reason this out, even if you don't remember these sign conventions. When you're sitting there in the exam, and I've given you some question about some system where you need to apply the first law of thermodynamics, and it says, The system does some work, and at the same time, there's heat added to the system, right? You think to yourself, okay, all right, well, I can think about each of these one at a time, right? And say, all right, if I add some heat to the system, what must happen to you? It must go up, therefore, heat added to the system must be positive. If the system does some work, it has to lose energy. So W must be positive in this equation because of the negative sign, right? In order for it to lose work. So like I said, even if you don't remember these two definitions, you should still, or these two sign conventions, you should still be able to reason it out in terms of the context of the problem.